Hello everyone, my name is V. Satvik. I am from CSE-D section. My roll number is 20951A05G3. Today my tech talk topic for operating system is cache coherence for GPU architecture. Introduction. Graphics processor units GPUs have become ubiquitous in high throughput general purpose computing. C-based programming interfaces like OpenCL, NVIDIA, CUDA is GPU computing by abstracting away the SIMD hardware and providing the illusion of independent scalar threads executing in parallel. Traditionally limited to regular parallelism, recent studies have shown that even highly irregular algorithms can attain significant speedups on GPU. Furthermore, the inclusion of multi-level cache hierarchy in recent GPU frees the programmer from the burden of software-managed caches and further increases the GPU's attractiveness as a platform for accelerating applications with irregular memory access patterns. GPUs lack coherence and require disabling of private caches if an application requires memory operations to be visible across all cores. General purpose chip multiprocessor CMPs regularly employ hardware cache coherence to enforce strict memory consistency models. These consistency models form the basis of memory models for high-level languages and provide the synchronization primitives employed by multi-threaded CPU applications. Coherence greatly simplifies supporting well-defined consistency and memory models for high-level languages on GPUs. It also helps enable a unified address space in heterogeneous architecture with single chip CPU GPU integration. Background. Baseline GPU architecture. An OpenCL or CUDA application begins execution on CPU and launches compute kernels onto GPU. Each kernel launches hierarchy of threads onto a GPU. Each workgroup is assigned to a heavily multi-threaded GPU core. Scalar threads are managed as a SIMD execution group consisting of 32 threads called a wrap. NVIDIA terminology or wavefront AMD terminology. GPU memory system. A GPU kernel commonly accesses the local thread private and global memory spaces. Software managed by local memory is used for intra-workgroup communication. Thread private memory is private to each thread while global memory is shared across all threads on GPU. Both thread private and global memory are stored in off-chip GDDR, DRAM and cached in multi-level cache hierarchy. However, only global memory requires coherence. The off-chip DRAM memory is divided among a number of memory partitions that connect to the GPU cores through an interconnection network. Memory access to the same cache block from different threads within a wavefront are merged into a single wide access by the cascading unit. A memory instruction generates one memory access for every unique cache line accessed by the wavefront. All requests are handled in FIFO order by the in-order memory stage of a GPU core. Writes the same word by multiple scalar threads in single wavefront do not have a defined behavior. Only one write will succeed. A GPU wavefront is similar to a CPU thread. GPU cache hierarchy. The GPU cache hierarchy consists of per core private L1 data caches and shared L2 cache. Each memory partition has a single bank of L2 cache. These L1 caches are not coherent. They follow a write no allocate caching policy. The L2 caches are write back with write allocate. Memory access is generated by the coalescing unit in GPU or core are passed one per cycle to the per core MSHR table. The MSHR table combines read access to the same cache line in from different waveforms to ensure only a single read access per cache line per GPU core is outstanding. Atomic operation. Read, modify, write atomic operations are performed at each memory partition by atomic operation unit. In our model, the atomic operation unit can perform read, modify, or write operation on a line resident in the L2 cache line in a single cycle. Consistency and coherence. A cache coherence protocol performs the following three duties. It propagates unitary return values to all private cached copies. It informs the writing thread or processor when a write has been completed and is visible to all threads and processor. Lastly, a coherence protocol may ensure write atomically, i.e. value from a write is logically seen by all threads at once. Write atomicity is commonly enforced in write invalidate. coherence protocols by requiring that all other copies of cache block are invaded before a write is completed. Memory consistency models may or may not require a write atomicity. Challenges of GPU coherence. Coherent traffic. Traditional coherence protocols introduce unnecessary traffic overheads to executing GPU applications that are designed for non-coherent GPU architectures. These overheads consist of recall traffic due to directory evictions, fault sharing, invalidation traffic, and invalidation traffic due to inter-kernel communication. Recall traffic becomes especially problematic for inclusive protocols on GPUs because the shared GPU L2 cache sizes match the aggressive private L1 cache size. An inclusive cache hierarchy is an attractive choice for low complexity coherence implementations. Moreover, the large directories required to reduce recall traffic in non-inclusive protocols take valuable space from GPU L2 cache. An effective way to reduce coherence traffic is to selectively disable coherence for data regions that do not require it. Elemental proposed a hybrid coherence protocol to disable hardware coherence for regions of data. It requires additional hardware support and code modifications to allow data to migrate between coherence domains. Storage requirements. With only tens of threads per core, CPU coherence implementations can dedicate enough on-chip storage resources to buffer the worst-case number of coherence requests. GPUs, however, execute tens of thousands of scalar threads in parallel. In CPU-like coherence implementation with enough storage to handle the worst-case number of memory accesses, a directory protocol would require an impractical on-chip buffer as large as 28% of the total GPU L2 cache for tracking coherence requests. Reducing the worst-case storage overhead requires throttling the network via back pressure flow control mechanisms when the endpoint queues fill up. TC-weak eliminates coherence messages and the storage of buffering them. Methodology. We model a cache coherent GPU architecture by extending GPU SIM version 3.1.2 with Ruby memory system model for gems. The baseline non-coherent memory system and all coherence protocols are implemented in SLICC. The MESA cache coherence protocol is acquired from Gen 5. Our GPU SIM extended with Ruby configured is to model generic NVIDIA Fermi GPU. We use Orient 2.0 to estimate the interconnect power consumption. The interconnection network is modeled using the detailed fixed pipeline network model in GANET. Two crossbars, one per direction, connect the GPU cores to the memory partitions. Each crossbar can transfer 1 byte, 132-byte flip per interconnect cycle. Two are from each memory partition for a peak bandwidth of 175 GB per direction. GPU cores connect to the interconnection network through private ports. The baseline non-coherent and all coherent protocols use the detailed GDDR5 diagram model for GPU SIM. Minimum L2 latency of 340 cycles and minimum DRAM latency of 460 cycles in 4 cycles is modeled to match the latencies observed on Fermi GPU hardware via micro benchmarks released by Wongtel. We use two sets of benchmarks for evaluation. One set contains inter-workgroup communication and requires coherent caches for correctness, and the other only contains intra-group work communication. While coherence can be disabled for latter set, we kept coherence enabled and use this set as proxy for future workloads which contains both data needing coherence and data not needing it. The following benchmarks fall into the former set: Burns at CUDA cuts, cloth physics, dynamic load balancing, stencil, versatile place and root. Conclusion: we find the conventional coherence implementations are not well suited for GPUs. The management of transistor state for thousands of in-flight memory access adds hardware and complexity overhead. Coherence adds unnecessary traffic overheads to GPU applications. Accelerating applications with both coherent and non-coherent data requires that the latter introduce minimal coherence overheads. We present temporal coherence, a timestamp based coherence frame network that reduces GPU coherence. We have proposed an implementation of this framework TCV, which uses novel timestamp based memory fences to reduce these overheads. Our evaluation source TCV is with simple lifetime predicted traffic MESA GPU 4 and GPU 6 directory coherence protocols 56%, 23% and 22% across a set of applications with coherent data. At TCV can enhance GPU providers programs with a well understood memory consistency model and simplifies the development of irregular GPU applications. Thank you.